Hi, my name is Paul Whitehead. I'm Professor of Water Science at the Oxford University Centre for the Environment. My background is very much as a mathematical modeller, developing tools and techniques that can be used to investigate hydrology and water quality and ecology in rivers and lakes. I've developed a model called INCA, which just stands for Integrated Catchment Model, and I use this as a tool to evaluate impacts of change, really, environmental change on the land surface and terrestrial environment, and what's happening in rivers and lakes, and the linkages between terrestrial systems and aquatic systems. The model is dynamic, so the idea is that you can assess day-to-day changes in behaviour rather than some annual average or seasonal component. And the advantage of that is that you can actually get to grips with a detailed understanding of what's going on within a catchment, how the different processes interact, and how the hydrology links with the water chemistry and the ecology. So I do computer modelling, and the advantage of the computer, of course, is that it's fast. And when you're dealing with very complicated catchments, there are so many things happening, so many variables changing, that it's almost impossible to understand all those interactions and all the complexity in your mind. So we rely on computers to do all the hard work for us. We try and simulate the physical and chemical and ecological interactions on the computer, and the computer will. The advantage of the computer is that you can repeat the run, so you can actually repeat a run, you know you're going to get the same result, and then you can alter things in an incremental way. So you could change the flow regime, or you could change the rainfall patterns, or you could change the parameters that control the reaction kinetics of the chemistry, and rerun the model so you can actually look at the incremental changes in the system and how that's affecting water chemistry and ecology. So that's why computer models are so useful. They basically provide a systematic way of analysing catchments. Of course, models can be quite complex, but that doesn't mean to say they have to be difficult to use. The other main objective of mine has been to make models user-friendly, so that you don't need to understand computer programming, you don't need to be a whiz at modelling, that you can actually run the models very simply using a nice user-friendly graphic system on the computer. Yeah, I'm going to show you the INCA model, which I said just stands for Integrated Catchment Model, for nitrogen in this case, and hydrology and ammonia, and we're going to set it up for the River Tweed, which is quite a large river. It's on the borders between Scotland and England, and is an interesting catchment because the headwaters are up in the Cairngorm Mountains, and then it flows down to the sea through agricultural areas. So it's an interesting catchment to explore. Okay, so what I'm going to show you is a model application to the River Tweed. So essentially we have to load the model, so it's an executable file, so we just click on this little icon here and the model loads. So the model is now loaded on the computer. Now we have to add some files. So we add a parameter file for the River Tweed, and this contains all the information on the reach structure, the land use, the nitrogen deposition, where the sewage works are, so all the information that characterise the catchment. So we just click on that and it should load the data, which it does. So each bar here represents a reach, and down the Tweed we have about 23 reaches, and these pie charts show you the land use, which is sort of forest upstream, and down at the bottom it becomes this kind of white arable area. And these pie charts represent the nitrogen and ammonia deposition from the atmosphere. Then we load another file, we load the data file, we click on that, and that basically gives us a time series. So here we have the actual rainfall over a 5-year period, 1994 to 2000 as it turns out. And here's what we call the hydrologically effective rainfall, so it's rainfall minus evapotranspiration. And here's the daily temperature over that period, and here's the soil moisture deficit. So when the soil moisture deficit is high, the soil is very dry. When it's zero, the soils are very wet. The third file we have to load is what's called the observation file. And this is just a file that contains all of the flow data, measured flow data in the river, and measured water quality data collected by the Environment Agency, or the Scottish Environment Agency. And when we've loaded, so we've now loaded those 3 files, and you click on this little icon here, this little man running, the person running, and you can see the model running. And it's basically moving down the river system, one step at a time. It's starting at the top end of the river, moving down one reach at a time, and solving all the equations that simulate the land, different land uses, and the river system, and slowly moves down these 23 reaches in the River Tweed. And it's running it for the whole period, 1994 to the year 2000. So it's now run the model, and it then fills up all of these icons with information. So for example, you can look at a 3D plot of the flows. So here's you can see kind of storm events moving down the Tweed. Here's a big storm event. So here's the top end of the river, and here's the end of the river before it enters the sea. And you can see the flows building up. And this is through time, so you can see a storm event moving down the river system. The other thing we can do is look at the what's happening down the river as a time series. So here you have a time series of flow from the model. This is a modelled output. So it's flow, nitrate concentrations, ammonia concentrations, and it's at reach 1. So that's right at the top end of the river in the mountain environments, basically. And we can move down the river one step at a time. So here's reach 2, reach 3. At reach 3 we start to get some data. So here's the observed, anything in red is the observed data, the measured data, which is either flow or water quality. And we can carry on down the river. So now we're reach 6, reach 7, reach 8, reach 9, and this is reach 11. And the main objective is the model reproducing the behaviour. So here, for example, the model's doing quite a good job of simulating the changes in nitrate. You see quite a drop off in the summer months as the concentrations decline, and then they increase during high flow conditions. And we can carry on down the river. Sometimes there's very good data, sometimes the data's not so good. It just depends on the routine monitoring. And we will need to check that the flows are being simulated adequately, and we're not doing a bad job of simulating those flows down the river system. Okay, so having assessed that the model is reproducing the observed behaviour reasonably well, it's never possible to get it perfect because we're dealing with a very complex system, and there's always measurement errors associated with both flows and water quality. But one of the great things you can do with the model is you can run a scenario. So let's imagine that the farmer at the top end of the catchment decides he wants to plough up the land. Pretty unlikely in the Cairngorms, but who knows with climate change. So we can go into the edit mode, we can go into the sub-catchment file, and we can look at the different land uses in this. So here's all the reaches, we're in the top reach in the catchment. You can see here we've got 24% forest and 76% of surface vegetation grazed, not fertilised. So that's like upland sheep, for example, grazing the upland moorland areas. Let's imagine the farmer wants to convert that upland pasture land to arable, so he wants to power it up and plant a crop. As I said, pretty unlikely, but this is just an experiment. So we can change that 76 to 0, and we can add that 76 back in as arable. We've changed the parameters, so we click on yes, and now we can just run the model again, but this time we run it as a scenario. And all we've done is change that land use in that one upland reach. We're repeating the run of the model. The software, the computer remembers the previous run. And so what we're going to do is compare the current run, which is the land use change simulation, with that previous run, and see what impact that change in land use would have had on water quality in the upper reaches of the river. So the model is run, and we'll go back up to. So we've gone back up to reach 1 now. So we're back at the source, and this is where we made the change of land use. And you can see the difference. That the blue line there is our original simulation. The green line is the scenario. So this is where we've changed the land use, and you can see the effect of doing that land conversion. You've massively increased the nitrogen in the water, up to 4 milligrams per litre when it was about 0.5 or maybe a maximum of 1. So you basically quadrupled the amount of nitrogen in the water column. And also you've increased ammonia. And as you move down the river, you can see the effect is still present. By the time you get down to the third reach, it's not having such an effect because of all the dilution of water coming off the hill slopes. And another way to look at this is as a profile down the river. So for example, this assumes that this is a snapshot down the river. So here's reach 1, reach 23. So it says on day 29 this is what the nitrogen would look like down the river system. And you can see here the high concentration on reach 1, and then it slowly dissipates, or rapidly dissipates, as you move down the river system. So that's just the effect of one change. But we can do all sorts of changes. We could run a new set of rainfall data through the model to look at perhaps future climate change. We could run a drought sequence through it to see how droughts might affect the flow and water quality. We could put in a new sewage works if they're going to develop a new town in the lower part of the Tweed. And so there's a whole sequence of different scenarios. You don't need a brand new computer, you just need a reasonably fast laptop, or you can run it on a desktop computer. We did design the whole model so it would run on a laptop and run fast, because we wanted to make it available to managers in the water industry, to students, to make it accessible to a large range of people. No, the basic version is available for free if you're going to use it for research or for teaching. If you want the full professional setup, you might have to pay a license fee. It just depends on whether you can build that into your cost program. But generally we give it away for free. Yeah, if you get in touch with me by email, I can discuss with you your requirements.